basic chemistry relies on highly predictable rules of atomic architecture. Moving across a row, adding protons pulls the atom tighter. Dropping down a column makes the atom larger. In the center, these trends break down. This is the transition metal zone, the D and F blocks. Here, elements with nearly identical outer structures behave like different materials. Understanding these materials requires looking past linear trends and examining the competing subatomic forces within the atom. This chart plots transition metal melting points across 3 periods. The data is volatile and nonlinear. We see sharp peaks for chromium, molybdenum, and tungsten, some of the most heat-resistant metals in existence. Yet 1 atomic number away, the melting point for manganese drops significantly. We see a similar disruption when we map the atomic radius of the D block. Moving right, adding protons should cause the atoms to shrink. Instead, the curve reaches a plateau. The elements maintain a nearly identical size, halting the expected periodic trend. These spikes in hardness and plateaus in size are the macroscopic effects of balanced subatomic forces. A metal's hardness depends on a lattice of atoms sharing a sea of electrons, creating metallic and covalent bonds. In transition metals, the number of unpaired d electrons dictates bond strength. More unpaired electrons allow for more bonds, increasing the melting point. We can see this in the electron architecture of chromium. Standard rules suggest chromium should have 4 electrons in the 3d subshell and 2 in the 4s, but the atom spontaneously moves one 4s electron to fill the 5th 3d slot. This half-filled state maximizes exchange energy. Chromium ends up with 6 unpaired electrons, ready to form strong bonds. Manganese also has a half-filled 3d subshell, but its 4s shell remains full with a pair of electrons. This configuration is stable enough that the atom resists sharing those electrons with its neighbors. Zinc reaches the extreme. Its 3d subshell is completely full. With 0 unpaired electrons available to bond, the metal is physically soft. High quantum stability inside the atom results in poor bonding outside the atom, explaining the valleys in the melting point data. The atomic radius plateau results from opposing forces. Adding protons increases inward magnetic pole, opposed by the shielding effect. As the inner d subshell fills, electrons push the outer shell away. Initially, nuclear charge is stronger, shrinking the atom. Mid-series, outward push cancels inward pull. At the end of the series, the sheer crowding of electrons causes repulsion to win, forcing a slight expansion. This flat line reflects a perfectly balanced subatomic stalemate. A distinct anomaly occurs when moving vertically from the 4d series to the 5d series. Zirconium and hafnium have identical atomic radii, even though hafnium has an entire extra electron shell. The atomic numbers between these elements jump by 14. Before the 5d series can fill, 14 electrons must populate the 4f subshell. Different orbitals block the nucleus with varying efficiency. S orbitals block well, while f orbitals are exceptionally poor shields. The f orbital is diffuse. It consists of complex lobes with massive gaps that let the nucleus pull through. This leads to the lanthanide contraction. The nucleus gains 14 protons of inward pulling power, but the 14 new f electrons fail to block that pull. This surge in effective nuclear charge pulls the outer shell inward, negating the size increase of the newly added shell. F orbital geometry dictates the scaling laws and physical properties of the heaviest elements. The actinide series experiences a more extreme contraction because their 5 f orbitals provide even less shielding. This extreme density and the resulting nuclear instability makes actinides like uranium the foundation of modern nuclear power. We use these forces in controlled reactors or witness their power when the nucleus is violently split. Transition elements provide physical evidence of quantum mechanics at work in the macroscopic world. Macroscopic variations rely on exchange energy, the effective nuclear charge, and shielding geometry. The hardness of a steel alloy and the dense fuel of a nuclear reactor are the direct results of the atom's internal quantum architecture.